Hello and welcome to Acumen Aviation's webinar. Acumen are a full-service asset manager with offices in Ireland, the USA, India and China. Today's webinar will be looking at engine maintenance reserves with an introduction to the Sparta MR calculator. We have 97 attendees today and I'd like to thank you all for taking the time to register and join us. Before we start, I would recommend that the presentation is viewed in full screen mode, and there will be some time at the end for any questions, followed by a short audience poll, and we'd appreciate your feedback. Before we start, let me just introduce myself. My name is Will Kynock, and I'm working as AVP Power Plant for Acumen, having joined in November 2017. I'm based out of the Dublin office and work within our experienced power plant team. I have 14 years experience working in the industry, the majority of which has been as a power plant consultant, working with a broad range of engine types, covering various projects for many of the world's leading lessors, investors and operators. During today's webinar, I'll be giving a brief overview of engine maintenance reserves and how they are different from other maintenance reserves before introducing the Sparta MR calculator. Using the Sparta MR calculator, I'll be demonstrating how changing several variables can impact maintenance reserve rates. I'll then move on to show several other features of the Sparta MR calculator, including the Sparta MR calculator mobile app. As with other reserves, engine maintenance reserves are accrued between maintenance events, building up a fund to be drawn down from at the time of a qualified event. The most simple way to calculate an engine maintenance reserve rate is to take the shop visit cost and divide by the estimated time on wing, giving a cost per flying hour. However, both the shop visit cost and the estimated time on wing are not fixed and vary from operator to operator, influenced by variables such as the hour-to-cycle ratio, operational environment and the use of D-rate. It's important to understand the effects of these factors when negotiating MR rates to ensure that the reserves are well funded at the time of the qualified event. Shop visit costs increase and time on wing decreases between shop visits with engine maturity, leading to an increased cost per flying hour. In other words, the maintenance reserve rate for a particular engine differs between shop visits. The MR calculator recommends a minimum and a maximum maintenance reserve rate, as well as a blended maintenance reserve rate. The blended MR rate gives the average rate across the engine's life cycle and takes into account the variation between shop visits. Airframe and landing gear reserves are not impacted by these factors and are far more predictable. The Sparta MR calculator is one of the modules from Acumen's asset management platform Sparta. Other modules include technical, records, maintenance and contracts, and all use cutting-edge technology such as artificial intelligence and machine learning. The MR calculator is the engine management module and is capable of modelling an engine's life cycle. The projections take into consideration factors such as hour-to-cycle ratio, operational environment and the use of D-rate. It's also possible to model the effects of changing the work scope, the engine build life, the monthly utilisation to investigate the impact they have on the engine life cycle, MR rates and cash flow. We can also use the MR calculator to project APU, landing gear and airframe maintenance reserves. To demonstrate some of the features of the MR calculator, I'll be looking at the impact of changing several variables on the maintenance reserve rates. The first scenario, we'll be looking at how changing the hour-to-cycle ratio can impact the maintenance reserve rates. The second scenario we'll investigate how a change in operational environment can impact the MR rates. And finally, the third scenario, we'll look at the use of D rate. For the first scenario, I'll be looking at a Trent 700 operating 400 hours per month in Southeast Asia. Example 1, we'll look at an hour-to-cycle ratio of 8:1, and we'll then look at the effect of introducing a short-haul rotation into the schedule, reducing the hour-to-cycle ratio to 4.5:1. For a Trent 700 operating at 8:1, the Sparta MR calculator estimates that the engine will operate for 36,888 flight hours first run, with the first removal in April 2027 and the first shop visit cost of $7.6 million. The second and third run intervals are approximately 32,000 hours, giving a blended MR rate of $258.45. Clicking the Analyze MR Cash Flow button shows the MR funds projection over the engine's life cycle. As we can see here, the reserves are accrued until each maintenance event, at which point they are drawn down from, reducing the overall balance. In this scenario, as we are charging the recommended maintenance reserve rate, the funds are always well funded. Let's have a look now at the effect of reducing the average hour-to-cycle ratio to 4.5:1. As we can see in the top left corner here, the first run interval is reduced from 36,888 flight hours down to 25,043 flight hours. The second and third run intervals are reduced from approximately 32,000 hours to roughly 21,000 hours. There's a small reduction in the estimated shop visit cost due to the lower number of hours operated, but the overall impact is to increase the recommended blended maintenance reserve rate from $258.45 to $383.88 per flying hour. Note also that the removals are earlier due to the lower number of hours. So we now have shop visits in 2024, 2029 and 2034 versus 2027, 2034 and 2040 at 8:1. So you'd be increasing the number of shop visits over the lease term. Clicking on the Analyze Cash Flow button again, we're able to model the effect of changing individual or multiple variables on the engine's life cycle and cash flow. All of the fields shown here with the pencil icon to the right can be edited, so we can look at the impact of changing the region of operation, the monthly utilization in cycles or hours, as well as the maintenance reserve rate and the LLP reserve rate. We can also introduce escalation for both the MR rates and the LLP rates, as well as escalation for the estimated shop visit costs and estimated LLP price increases. If we look here at changing the monthly utilization, so the hour-to-cycle ratio is reduced to 4.5:1, and by clicking Simulate Scenarios, we can see that the engine shop visits are earlier than 8:1, and on the far right-hand side, the reserve funds are underfunded from the first shop visit onwards. This can be clearly seen in the graph on the same page, which overlays the funds projection at 4.5:1 over the original projection at 8-1. As you can see here, the reserves are accrued at the same rate because we're charging the 8-1 MR rate, but the shop visits are earlier, and we end up with the reserves underfunded at each shop visit and 3 shop visits at 4.5-1 in the same period that we had 2 shop visits at 8-1. To summarise, the hour to cycle ratio can significantly affect the interval between shop visits. Operation at a lower hour to cycle ratio reduces the interval between shop visits, whilst a higher hour to cycle ratio will increase the interval. A seemingly small change in route structure, such as introducing a 1 or a 2 hour flight to the schedule, can reduce the overall average hour to cycle ratio and lead to the reserve funds being underfunded at the time of each qualified event, and an increased number of shop visits over the lease term. Moving on to the second scenario now, and we'll be looking at a CFM 56-7B 26/3 operating 300 hours per month at an hour to cycle ratio of 2-1. We'll first look at operation in Central Europe, and then the impact of changing the operational environment to the Middle East. Firstly, in Central Europe, the MR calculator estimates that the engine will be capable of operating for 33,138 flight hours first run. At the first shop visit, the engine will be built for 13,431 flight cycles, matching the fan LLPs, with the core and LPT overhauled at a cost of $3.3 million. The second and third run interval is estimated to be approximately 27,000 hours, and the overall blended maintenance reserve rate is $129.98 per hour. By comparison, if we operate the same hour to cycle ratio, the same level of D rate, and the same engine type in the Middle East, the estimated first round is almost half that of Central European operation, down to 17,404 flight hours from 33,138. Due to the lower number of cycles operated, the first shop visit in the Middle Eastern operation is for a core-only work scope. However, the shop visit cost, due to the higher expected scrap rates, is actually more than it would be for a core plus LPT work scope in Europe, up to $3.4 million from $3.3 million. The second and third shop visit intervals are reduced to 14,500 hours from 27,500 hours, so again almost half, and the overall impact is to increase the recommended MR rate from $129.98 to $266.88 per hour. Again, if we look at the Analyze Cash Flow page and change the variables, clicking on the Simulate Scenarios button, we can see that the engine removals are earlier and the funds are underfunded from the first shop visit onwards. Again, the change in operation can be modelled and overlaid onto the MR funds projection for the Central European operation. And we can see in this example, not only have we got underfunded reserves from the first shop visit onwards and earlier removals, we now have 3 removals in the Middle Eastern operation before we have reached 2 removals in the European operation. To summarise, operation in harsh environments reduces the interval between shop visits and increases the shop visit cost, leading to an overall increase in the recommended maintenance reserve rate. Finally, for scenario 3, we'll be looking at the effective D rate. We'll be looking at a V2527-A5 Select 1 operating 300 hours per month in North America and an hour-to-cycle ratio of 1.5 to 1. For the first example, we'll be looking at an engine operating with 0 D rate. And for the second example, we'll be looking at the impact of operating with 20% D rate. For the engine operating with 0% D rate, the MR calculator estimates that the first shop visit interval will be 17,253 flight hours with the first removal in June 2024. The second shop visit is estimated to be second and third shop visit intervals are estimated to be approximately 14,700 flight hours with a blended MR rate of $209.76 per flight hour. If we reduce or increase the level of D rate to 20%, the first run interval increases from 17,253 flight hours up to 20,630 flight hours, and the second run and third run intervals are increased to 17,600 flight hours from 14,700 flight hours. In this scenario, the overall impact is to reduce the recommended blended maintenance reserve rate from $209.76 to $183.70 per flight hour. Again, we can overlay this onto the original MR funds projection, but in this instance we can see that the interval between shop visits is increased. We're accruing reserves at the same rate as we're charging the 0% D rate maintenance reserve rate, and the engine removals are later. So at the time of each qualified event, there's a much healthier fund balance, and we're always well funded. Operators vary D rate between aircraft depending on their route structure. So using the MR calculator, we're able to generate a matrix such as the one shown here, which shows the recommended blended maintenance reserve rates at a range of out-of-cycle ratios and a range of D rates. Clicking on the LOI MR table button, we're then able to select the increment between the out-of-cycle ratios. In this instance, we've selected 0.1, giving us a range of 1.1 to 1.99 for the out-of-cycle ratio. We can then select up to 4 levels of D rate and generate the table shown. The table can be exported and used in contracts or for negotiation. To summarise, the use of D rate can lead to an increased time on wing and decreased shop visit cost, reducing maintenance reserve rates. Operators vary the use of D rate between routes and aircraft, and it's possible to generate a matrix showing MR rates at a selected range of D rates and out-of-cycle ratios using the MR calculator. I'm now going to demonstrate a few of the other features of the MR calculator. The first one here being the cash flow. Clicking on the Generate Monthly Cash Flow button, we're able to show the accrual and build-up of maintenance reserves over a selected period. In this example, we're showing a period around a shop visit. So we have an increase in reserves monthly, and then At the time of the shop visit in May 2025, a reduction of $3.1 million to cover the shop visit cost. There's then a period of 3 months where the engine is not accruing reserves as it's assumed to be in the shop, before being reinstalled and accruing reserves again from August 2025 onwards. The MR calculator can be used to model an entire aircraft and will show cash flow for airframe, landing gear and APU reserves, as well as engine maintenance reserves and LLP reserves for each engine. In this case, we've selected engine number 1 shop visit only. We can also show the cash flow from the start of the lease over the whole engine life cycle and select any period we want to display. The fund status can be shown at any date on the MR funds projection page. By selecting a date, as shown in the left-hand side there, we can generate the reserve fund status on that particular date. For example, here we started in March 2021 and we have an estimated fund balance of $1.8 million. The fund status in March 2023, following 2 years of accrual, has increased to $4.1 million before reducing in June 2025 following the first shop visit. The funds then accrue following the first shop visit, and the date shown here on the 15th of March 2028 show $2.3 million in the reserve fund. For the post-shop visit balance, there's actually, in this example, the funds are underfunded by $668,000, and this illustrates the lessee or the lessor's exposure at this shop visit. There's 2 columns here, on the left-hand side showing the total fund, and on the right-hand side showing engine number 1. If we're modelling an entire aircraft, the total funds will show the funds of all of the reserves that are selected. So that could be aircraft, airframe, landing gear, APU, all of the engine shop visits and all of the engine LLP reserves. We've then selected in the right hand column just engine number 1 shop visit, which is why in this case both reserves are the same balance. It's also possible to change the work scope and build life to investigate the effect that has on the engine's life cycle and MR rates. In this example, we're looking at a 5B4/3 operating in North Oceania at 1.5 to 1 for 300 hours per month. At the first shop visit, the engine is built for just over 14,000 cycles, limited by the fan LLPs. The estimated shop visit cost is $3.8 million, and the blended maintenance reserve rate in this scenario is $216.08. If we unclick the LPT box, the engine is built for 9,000 cycles, limited by the LPT LLPs. The estimated shop visit cost is reduced to $3 million. And the overall impact on the blended MR rate is a reduction from $216.08 to $210.09. This feature allows power plant engineers to change the work scope and build life easily to see the effect over the engine's life cycle. The Sparta MR calculator is also available as a mobile app on Android and Apple devices. The screenshot shown here on the left-hand side show the selection of the engine type, followed by the selection of the operational region and the selection of the hour to cycle ratio. We're then able to determine the work scope at each shop visit and generate the next page, which shows the estimated shop visit cost, the estimated blended maintenance reserve rate, and the estimated time on wing. final screenshot shows the engine's life cycle forecast and reserves. To summarise, engine maintenance reserves are influenced by a number of variables, including operational environment, out-of-cycle ratio, and D-rate. The Sparta MR calculator takes into account these variables to estimate the optimum rates over an engine's life cycle. Acumen Aviation's Sparta asset management platform has several modules available for subscription, including the MR calculator, which is able to model and recommend optimum MR rates. I'd like to thank you for your time today and for attending today's webinar. For more information about Acumen, the MR calculator, or the entire Sparta asset management platform, please contact us using the following details. At the end of this webinar, there will be a short audience poll, and the webcast will be available on Acumen's podcast in the next week. I'll now address some of the questions that have been raised during the webinar. First question here. So we've got a question here that's asking, so all of the examples appear to show new engines. Is it possible to model a mature asset? Yes, it is. So when we're building the engine at the start of the projection, we can input the last shop visit, we can edit the LLP stack, and the number of hours operated since last shop visit. It's also possible to add an MR fund balance at that time and project the engine forward, taking into account the previous operation. The next question here, is it possible to arrange a live demo? Yes, absolutely. If anyone's interested in a demo, then please contact us using the details shown here, and we can arrange that. So a couple of questions here regarding the shop visit costs and time on wing estimates. The MR calculator is a statistical model, and we're constantly comparing and using real-world data to train the model. As engines become more and more reliable and the shop visit costs continue to increase, and the MR rates are changing frequently. So we have to continue to review and compare the data that to ensure that they're correct. We're running out of time now, just up to end, but for all the outstanding questions that weren't answered, I'll take them offline and reply directly to each attendee. So thank you once again for attending. I hope you found the presentation interesting, and yeah, thanks very much.